role of b in a sinusoidal function. So we've figured out what happens when you have a multiplying number on the outside of the function. What if I take a number, though, and multiply it by the x on the inside? What effect will that have on the graph of the function? Well, once again, let's turn to the graphing calculator and investigate. I'll start again with the regular sine function using that z-trig option. And here's our familiar graph, period of 2 pi, amplitude of 1. Now let's go back to the y equals area and add in sine of 2x. Y equals sine 2x. We're wondering what impact that 2 will have on the graph. I'll add it to my picture. Okay, well this time it looks like somebody has taken the blue graph and squished it in from the sides, from the left and right. It's been horizontally compressed. What about our features? Well, the amplitude looks unchanged. The red graph still has an amplitude of 1. That shouldn't surprise us. In both of the equations I just typed in, the a value was 1. So of course the amplitude is 1. What about the period? Well, you can tell because this thing has been squished in, it starts to repeat much earlier than the blue graph. The blue graph took all the way to 2 pi. The tick marks are somewhat hidden, but here's pi over 2 and here's pi. That's the distance the red graph travels before it repeats again. So the period of the red function is pi. We've used a large number like 2. Now let's see what happens if we use a small number like 1/2. I'll go back to the y equals and replace that second equation with sine 1/2 x. And then we'll add that to the graph. Well, this time, instead of the graph compressing, it looks like somebody took the blue graph and pulled it out to the right and pulled it out to the left. It's been stretched horizontally. What about our features? The amplitude is still 1. Again, that's not surprising. How about the period? That's actually a little harder to tell in this picture. Let's see, the first hill takes me all the way out here to 2 pi, the former period of the blue function. Well, that means the valley will take another 2 pi, and I'll end up here at 4 pi. 4 pi out here somewhere would be the period of the red function. So bigger values of b seem to shrink the period. Smaller values of b, less than 1, seem to increase the period. Of course, we want to know, is there a pattern to this? And the answer is yes, there is a connection between the new period, the old period, and the value of b. You might have to do a few more examples in order to figure out that connection on your own. Let me tell you what it is. The new period can be found by taking the old period, 2 pi, of the regular sine or cosine function, and then dividing it by the b value. You can test that out in our examples. Here the b was 2, and sure enough, if you take 2 pi and divide it by 2, you end up with pi. Here the b was 1/2. If you take 2 pi and you divide it by 1/2, let's see, dividing by 1/2 is the same thing as multiplying by the reciprocal of 1/2, which is 2 over 1. And of course, when you do that, you end up with 4 pi. P equals 2 pi over b. Okay, so let's summarize. B determines the period. B is not equal to the period, but it influences the period in the following way. We have learned that the period will be 2 pi divided by the value of b, or expressed as an equation, p equals 2 pi over b. Make sure you learn this equation very, very well. We also notice that larger values of b values that are bigger than 1, result in a horizontal compression toward the y-axis, while small b values that are less than 1, result in a horizontal stretch away from the y-axis. Thanks for watching.